Hello and welcome to another exciting lecture for statistics. In this lecture we will be talking about one sample test. So we're now looking at our first true inferential statistics test. So we're going to look at one sample test for means and correlations. Correlations can also be done in a way looking at proportions. We haven't covered correlations in here yet. We'll cover that in a couple weeks. But right now we'll look at the tests we can do to see if a correlation is significant or not. So when we're talking about one sample test, we're going to look at a couple different types of tests. We're going to look at z-tests, which we've already kind of covered a little bit. We looked at last week we looked at how to do z-scores for looking at it for probabilities and inferential statistics. Well, now we're going to actually do z-tests for significance. And we'll also look at t-tests as well. We'll look at them for both means and correlations. And one of the things we'll look at in a few slides here is the 8 steps of hypothesis testing, which is something you'll do for all tests for the rest of the semester, except for confidence interval tests. So all hypothesis testing tests are going to use these 8 steps. I'll go over them a couple times and you'll get the chance to see a couple examples in this set of slides of them. So when we're looking at this, for means, we're going to look at the population mean, we're going to look at hypotheses, and then we'll look at one sample z and t tests for means. And then we'll look at correlations as well, look at the hypotheses there, and the one sample z and t tests for correlations. And as I said already, the correlation test also works for proportions. So they are very similar tests. And we don't do too much with straight up proportions, but we do a lot with correlation in the sciences. So when we look at this, we'll look at how to determine if a correlation is significant, as well as determine if a correlation is significantly different than a hypothesized value. So when we're doing hypothesis testing, one of the things I talked about last week is directional versus non-directional, one-tailed versus two-tailed, and what the basically different sets of symbols you could have. And I'm going to go over those just one more time real quick on this slide because it leads into what we're going from here, but it's really good to know this. First off, recall that the equality always goes in the null. So I'll put this in light blue, but the equality always is going in the null hypothesis. So the light blue you see there is where the equalities are. It's equal, less than or equal to, or greater than or equal to. And they're all in the null hypotheses. Now, when you're doing an alternate hypothesis and a null hypothesis, they are basically the opposites. So if the null is equal, the alternative is not equal. So this is one set of symbols you can have. If the null is less than or equal to, then the alternative has to be greater than. If the null is greater than or equal to, the null has to be less than. So those are the 3 different sets. The issue here though is that these bottom 2 are directional or one-tailed. The top one is two-tailed or non-directional. Why is that important? Well, that'll be important because whenever you're looking at the tables, the charts, you need to know whether it's one-tailed or two-tailed, whether it's directional or non-directional. So one of the steps of hypothesis testing that we'll get to in a few slides is stating whether your hypothesis is directional or non-directional. When we're looking at what's on this slide, the final thing, I've got lots of different colors here. Let's put the last color as purple. That is, I'm going to just point out here that what we are looking at when we're looking at one population mean, what this hypothesis is essentially saying. So we'll look at the non-directional one up at the top. The null hypothesis is saying that our mean that we're testing. So this will be the mean essentially from our sample. Why is this a population symbol though? Because when we're doing inferential, we're basically implying that it's the population. So our population mean is in this case for the null, equal to the null mean. The null mean, what is the null mean? That is the hypothesized mean. So the one on the left of the equal symbol, the one with the x, that is from our sample. The one on the right, that is whatever we're hypothesized comparing it to. So if I said that I was wondering if the average age of Detroit Mercy students differed from the national average of college students, which is 22. Let's say it's 22. I don't know if that's exactly what it is, but let's say the national average is 22. Well, in that case, what you would have is here in this top one, you'd have your HO would be the mean of UDM is equal to 22, because the mean with the O next to it is essentially our hypothesized mean. And then of course with the one below it, you notice I did HA instead of H1. Again, they're interchangeable. Our mean of UDM is not equal to our hypothesized mean of 22. And that's, so if the researcher's just trying to see if the average age of Detroit Mercy students differs from the national average, then that would be the way we would write our hypotheses. So the important thing here is on the left is, in a sense, it's going to stay the mean symbol, but on the right, the mean with the O next to it, that is our hypothesized mean. Now, how are we doing this? How do we do this? Just like I talked about last week, when we're doing inferential statistics, we're looking for our critical values based on probability. How do we do that? We do that through a sampling distribution. We've got this sampling distribution here. It's sampling distribution of all possible means you could get from drawing a sample from the population. And then our critical values, in this case, this is a non-directional because it's got alpha on both sides. We would then figure out what our critical value is for the probability that the results we get are due to chance are extreme, more extreme than our alpha. So in this case, we need to see that what we're researching, what we did the study on, our sample, to see if it falls in these gray regions, these extreme regions, and then we reject HO. Next thing to talk about is this concept of population variance known and unknown. So we're going to do two different types of tests. The first one is going to be this one sample z-test for the mean. And in this test, we know that if the population distribution of x is normal and the population variance is known, we can do a z-test based on the standard normal distribution. So we can do a z-test based on basically our charts from the z-charts. We can then figure out what the critical values are based on that. However, there's a very important thing here, and I'll come back to this when we're talking about the t-test. The population variance needs to be known to do a z-test. So if the population variance is known, you do a z-test. If the population variance is not known, we'll talk about this later, but the population variance is not known, we estimate it and we do a t-test instead. Because in the process of estimating the population variance, it causes the distribution to change slightly. So we can't use a z-distribution if we don't know the population variance. So that's the big decider. If on a test you come up and you're given a problem, and the problem straight up says the population variance is unknown, then you can't do a z-test. But if it says the population variance is known, and it's the population variance equals x, whatever it is, then you do a z-test. If possible, we always do a z-test over a t-test. It has more power. We talked about that at the end of the last set of slides. Things power. Well, z-tests have more power than t-tests. So we do a z-test if we can. However, in the real world, population variance is rarely known. So it is very rare that you'll do a z-test in the real world. we're looking at them here because it's the first test you should do, and it kind of links what we did earlier with we did z-scores and stuff like that. Now it links that into hypothesis testing, but in the real world you rarely do a z-test for hypothesis testing. You'll typically do a t-test. For our formula for z, it's the same thing we used last week when we started to look at the standard normal distribution with the sampling distribution of x, so the sampling distribution of the mean. We use this formula, and it's just a z-score transformation applied to the sampling distribution of the mean instead of to raw scores. And again, just like last week, recall that how these formulas work out. In the end, our z-score formula that you're going to use for hypothesis testing is down here. The same thing we used last week when we started looking at probabilities, but now we're going to look at them in the context of using them as a means of seeing if our value is more extreme than our alpha, meaning we would reject our null hypothesis. Here is that 8 steps of hypothesis testing that I said I'd come back to. And this is important. On the homeworks, on the next 2 quizzes, every problem where you're doing hypothesis testing, you have to do all 8 of these steps and you have to label them. So this is a required thing to do. If I can write properly. So this is required. This will be required on all hypothesis testing problems for the rest of the semester. Now, don't be intimidated by this. It's not actually as much as it looks like, but let's go through this real quick. Step 1 is state the null and alternative hypothesis. Again, just like I said last week, it's easier to state the alternative hypothesis first and then the null because the null is the opposite, but step 1 is where you state your hypotheses. Step 2 is you state which test you're doing. I'm not as picky as I could be on this, as long as you tell me what test you're doing. So this first test we're going to be looking at is a 1 sample z-test. Technically it would be a 1 sample z-test for sample means. But as long as it's being communicated that it's 1 sample and that it's a z-test, you're good. Why is that the case? Because next week we'll do 2 sample z-tests. And at the end of this chapter, after we do z-tests, we'll do 1 sample t-test. So both of those need to be done to differentiate. Now technically we're going to do 1 sample z-test for the mean and 1 sample z-test for the correlation, but as part of the problem, I'm going to understand that it's a difference between mean and correlation. So just as long as you're putting 1 sample z-test, 1 sample t-test, and later on 2 sample t-test, 2 sample z-test, that type of thing, you'll be good. Step 3 is a very easy step. That is, indicate whether the test is directional or non-directional. You can also say one-tailed or two-tailed. Either is fine. And to determine this, you just need to go back to step 1, look at your hypotheses, and determine whether it's directional or non-directional from your hypotheses. And again, if you've got equal and not equal, it's non-directional. If you've got a greater than or less than symbol in there somewhere, then it's going to be directional. Step 4 is easy but can be tricky, and that is first we're going to specify your alpha. Your alpha will always be in the problem, and I'm pretty sure for everything I do on both the homework and the quizzes, it's always an alpha of 0.05. But that being said, you need to specify your alpha. So it'll be in the problem, but specify your alpha. Specify your n, your sample size. So you need to list your n. And then finally, you list your degrees of freedom if appropriate. We're going to get to it in just a minute, but degrees of freedom is necessary for a bunch of different tests, but not in some tests. Z-tests do not use degrees of freedom. It's the only test we'll use in here, other than some of the non-parametrics, that do not use degrees of freedom. So the z-test, you would put degrees of freedom not applicable, or you could just have nothing there, as long as you're not putting a degrees of freedom. If you put a degrees of freedom on a z-test, then you get points off because it's not appropriate to put degrees of freedom for a z-test. And degrees of freedom for each test differs, and we'll get to that when we get there, but like this week, degrees of freedom for the t-test, the one sample t-test, will be n-1. Degrees of freedom for the one sample t-test for correlation will be n-2. So there's two differences there, but we'll get to those. Step 5 is the long step. Step 5 is where you actually calculate out your test statistic, your observed value. You run the statistical test. So this is where you take your numbers, your mean, your standard deviation, all of that from your sample, run it through your equation, and you get your observed value. For a z-test, this will be your observed z value. For a t-test, this will be your observed t value. I'll show that in a couple slides. Step 6 is obtain the critical value from, and it says tables in the textbook, but tables and charts. So I've already given you the z charts. I'll give you the t chart in this set of slides, but you need to obtain the critical values from different tables. You can go, again, same thing, you can go online and Google z table or t table and get those charts as well. So it's wherever you obtain the critical charts, that's up to you, but obtain the critical value, what does that mean? That means you need to take your alpha, your degrees of freedom, if applicable, if it's relevant, and whether it's one-tailed or two-tailed, and get the appropriate critical value. I'll show you that again in a couple slides. Then step 7 is make a statistical decision. So step 7 is if you compare your observed to your critical, if your observed is equal or more extreme than your critical, we're going to reject HO. And an important note here is, why don't I just say is greater than, if your observed is greater than your critical? Because sometimes your observed and your critical values are negative. So it needs to be more extreme, and the signs need to match. What does that mean? It just needs to mean if your alternate hypothesis is basically saying that greater than, then your observed value needs to be greater than your critical value. If your alternate hypothesis is saying less than, then your observed needs to be less than your critical in the negative direction, more extreme in the negative direction. But signs need to match your alternative hypothesis. If not, you fail to reject. And then step 8, and this is one where a lot of people get wrong, you need to state the conclusion in words. You need to interpret the results in words. I'm going to have examples on these slides of various different ways to state step 8, but just saying it's significant is not enough. So looking at that step 7 a little bit more, and that is the rejection decision. So this is step 7. We'll first look at two-tailed tests. Two-tailed tests are really easy, and that is if the absolute value of your observed statistic is greater than the absolute value of the critical, you're going to reject HO. Two-tailed tests, you just use the absolute values. So just drop off any negative signs. You still need to put the negative sign in step 5 and 6, but in step 7, you're just using the absolute values. If your absolute value of your observed value is less than your critical absolute value of your critical value, then you would fail to reject HO. You see sometimes here it says do not reject. I prefer the terms, the saying fail to reject rather than do not reject. And again, why is this the case? Because in our two-tailed, you've got your critical values, your critical z's that you see here. You're going to have a upper critical z value and a lower critical z value. And you see the gray is more extreme than that. So anything in the gray here is going to be greater than this upper critical. anything in the gray here on the lower end is going to be less than this lower critical. But if you took absolute values, it would be greater than. So in a sense, the easy way to do two-tailed testing for non-directional is just take absolute values, and if your observed is greater than your critical, then you reject. For step 7 for one-tailed tests, for this, you have to do a little bit different, because if the first thing is if the signs are different, then we fail to reject. What does that mean? That means if, let's say, I was asking, does the average age of Detroit Mercy students, is it less than the national average? So the alternate hypothesis is less than. If my observed value is positive, that means the actual average age of Detroit Mercy students is greater than the national average. So the signs wouldn't match. And I'm trying to see if it's less than, and the null is going to be if it's equal to or greater than. If the signs are different, that's going to mean it's greater than. The signs don't match, that's going to fail to reject. If, on the other hand, I have this hypothesis that the average age is less than the average, and I run my test and I get a number that's less than 0, a negative number, that is going to, in a sense, be the signs matching. So now if the signs are the same, if the signs match, we need then the absolute value of our observed to be greater than our critical to reject. If not, then you would fail to reject. So if HA is less than, then observed has to be negative to reject. If HA is greater than, then observed has to be positive to reject. So the reason I'm going over this a little bit extra is because some people get confused by this. I don't want you to get confused by this, so I kind of restated it a few different times. Let's actually run through 8 steps of hypothesis testing. I'm not going to write these fully out when I'm doing the review for the exam. I'll have them where I write them fully out. I've got them fully out already on the slides here just for your ease. So it's going to be a little bit quicker that we'll be able to go through these. But let's look at this first test. Assume that the scores for employment test are normally distributed. So again, tests like the z-test and the t-test have that assumption of normal distribution. They have to be normally distributed. You can use essential limit theorem if your sample size gets large enough, but with this one it's got a sample size of 25. It's a little bit low, so it might be skewed one way or the other if with it being that low and then it being not ending up being normally distributed. However, on the problem here it states the tests are normally distributed, so that assumption is met. It has the population norms. So the population standard is a mean of 100 and a standard deviation of 15. So now we got the first question. Do we know population variance? Well, population variance is just going to equal our population standard deviation squared. We've got our population standard deviation, therefore we have a population variance. Population variance is known. Since population variance is known, we do a z-test. So we've got this population variance known, we're doing a z-test. The company hires a researcher to determine if the average score of employees differs from the norm. So we can already look at this and look at and start thinking about our hypotheses. They'll be on the next slide, but let's just look at these and the logic of how we create them. We are going to have the mean of the company. So we'll just look at mean of the company, and as I said last week, it's best to do the alternate hypothesis first. In this case, the researcher needs to determine if the average score of employees at the company differs from the norm. So that means we're trying to see if it is different than one direction, two direction, directional, non-directional. We're not saying greater than or less than, so it's non-directional. So we're going to be not equal to the population norm, which is 100. Therefore, the null is equal to 100. And we've got then a sample of 25 employees. So our n is going to equal 25. Our mean is going to be equal to 105. Down here, we're going to use an alpha of 0.05. And it's a z-test, so degrees of freedom are not applicable. Let's actually flip slides, and you'll see a lot of this written out already. I just want to kind of look at how you pull this information out of this problem. So we've got our hypotheses here. That is our null and alternate hypothesis. And again, the alternate is that our mean is not equal to 100, then the null is equal to 100. Then we've got our test. Our test, we are doing a z-test. So this would be a one sample z-test for the mean. So it's, again, this is, in this one, the problem here, it's just saying sample mean z-test because the population variance is known, it's justifying it. I'm not super picky on this as long as you're doing, as long as I understand what test you're doing. And this is a good point to stop for just a second and explain one of the things that's a big deal when it comes to me grading homeworks and exams. And I'll restate this when I'm doing the exam review. But the thing is that if you get step 2 here wrong, if you get step 2 wrong, you're likely to do step 4 wrong. And you're likely to do step 5 wrong, step 6 wrong, possibly even step 7 wrong. I am not going to mark you wrong for every step you do wrong if you do the wrong test. So if instead of doing a z-test here, you decided to do a t-test, I would then mark you wrong for this step, and then I would grade the rest of the problem based on if you were doing a t-test instead of a z-test. Therefore, you don't get, it's not a double whammy, triple whammy, you just don't keep getting hit over and over again just because you decided to do the wrong test. If you decide to do the wrong test, if you make the decision to do the wrong test, then you'll get points off for this step, doing the wrong test, but the rest of the steps will be graded on the test you did rather than the test you should have done. Which also gets to, okay, step 3 is, this is two-tailed or non-directional. Our hypotheses are non-directional. Let's say you did the hypotheses wrong, and you did the hypotheses as, instead of equal and not equal, you did the hypotheses as the alternate as greater and the null is less than or equal to. Well, then in step 3 here, you're going to say it's one-tailed or directional. I'm not going to mark you wrong for both of them. I'll mark you wrong for the hypotheses because you did them wrong, but then I'll grade step 3 based on what you said in step 1. So I'm not going to keep hitting you for making the same exact mistake. You'll get hit once for making that mistake, and then after that I'll grade it based on what you did with that mistake. It takes extra time for me to grade, but I don't think it's fair to you at all for me to mark you over and over and over again for the same mistake, especially since on the exam these will be worth like 15 points total for the one problem, and if you do like step 2 wrong, you might get steps 2, 4, 5, 6, and 7 wrong, and then if I marked you wrong for each of those, that would be 10 out of the 15 points you'd get wrong. Instead, I'd mark you wrong for 2. You might get 2 points off, but then get the rest right, 2 or 3 points off on step 2, and get all of the rest right based on the doing the wrong test, but I grade it based on that test. I hope that makes sense, but that's, and like I said, I'll repeat that again when I'm doing the exam review. So, again, step 1 here, null and alternate hypothesis. Step 2, state the test. Step 3, directional or non-directional. Step 4 is alpha n in degrees of freedom if applicable. So our alpha here is 0.05, our n is 25, and our degrees of freedom are not applicable. If perchance you didn't write this at all, you just didn't put degrees of freedom in at all, then I won't mark you wrong. That's technically a correct way to do it. Degrees of freedom not applicable, degrees of freedom equals NA, all different ways you can say it, as long as you don't write degrees of freedom equals and then a number. Because if you write degrees of freedom equals a number, you'll get points off here, because for a z-test, degrees of freedom is not applicable. Step 5, we do our statistical test. So this is where you go back to that z-test. We're doing a z-test, but you go back to that z-test we looked at before. You pull in the formula, and you just plug in the numbers into the formula. So let's look at that. Our formula is here on the center left, and then we just plug in the values. So our mean is 105. Our hypothesized mean here, so this should be mean 0. Our hypothesized mean is 100. Our population standard deviation here is 15, and our n is 25. Do the math, you get 1.667. This is a interesting number because it's between two different numbers, but we'll come back to that. But our observed score, our z observed, is 1.667. I'm going to ask on the homework and test that you circle this number, because the stuff above it, it's easier for me to find as long as you've numbered them. So you do have to number them. Numbering is important. But when you get to step 5, you're going to have a whole bunch of writing, a whole bunch of math done. This did it really simple, but you could take more steps and more steps. If you circle your final answer, it'll make it really easy for me to find. So our z observed equals 1.667. We've got the first 5 steps here. Step 6, find our critical value. So to do this, we need to use a z-score table. We did this last week, so I'm not going to go over it too much again this week. But for the two-tailed test with an alpha of 0.05, you need to do alpha divided by 2 because the alpha is split between the tails. Alpha divided by 2, so 0.05 divided by 2 is 0.025 here. And that's in each tail, 0.025 in each tail. You then need to go to the z-score table and find 0.025 and find the z-score associated with 0.025. You don't look for the z-score of 0.025. You look for the area of 0.025 that's in the gray area. So it's either in the extreme right tail if that's in your chart, or extreme left tail if that's in your chart. Remember, it's symmetrical, so it'll be the same on both ends. But we're looking for, let's say you're using the cumulative here. The cumulative would be at and below that point, so in that case we would use this one. And we go to find the area, the cumulative proportion, that is the values inside the chart, not on the edges, but inside the chart. You find 0.025, and you find the z-score associated with that, and the z-score for it is negative 1.96 and 1.96. Again, it's symmetrical, so it's going to be the same on both ends. Therefore, when we're talking about, we talked about earlier, how we're talking about more extreme. Well, we're doing a non-directional test, so we would just use absolute values. But what we're trying to see now is our observed value more extreme? In a sense, when I say more extreme, I mean, is it greater than our critical value? Our critical value is 1.96. If you remember, our observed value was 1.667. For non-directional tests, we use absolute values of them, so the sign doesn't matter. So 1.667 is not greater than or equal to 1.96, so therefore we fail to reject HO. If it had been greater, if our observed value had been greater than 1.96, this is where we would say reject HO. But it's not greater than 1.96, therefore we fail to reject HO. And then we state this out in terms of the problem, that is given an alpha of 0.05 and a z equals 1.667. This is basically APA style of saying statistics. Given an alpha of 0.05 and a z equals 1.667. So you've stated back out what's there, what you found, and your alpha and what you found. We now say fail to reject HO and conclude that there's insufficient evidence to indicate that the average score of employees is different than the norm. There's a couple big things here. First off, we restated whether we rejected or failed to reject. So in this case, we failed to reject, so we restated that we failed to reject. We also said it in terms of the problem, so average score of employees is different than the norm. We don't know that. We can't say that. We can't say it's different than the norm because we failed to reject. If we'd rejected, we would have said it's different than the norm. There's specific verbiage we would have used, but if we'd rejected, we would have said it's that the average score of employees is different than the norm. Since it's not, we cannot say that. Instead, when we fail to reject, these are two important words you use. Insufficient evidence. So, in a sense, when you're failing to reject, you're saying there's insufficient evidence to indicate that our alternative hypothesis is supported or that our alternative hypothesis is true. You should never, when you fail to reject, use the words significant. We'll get to that when we reject in a little bit, but when you fail to reject, never use the word significant in your step 8. Insufficient evidence, that's the appropriate way to basically state it if you fail to reject. Okay, let's look at another example. But now we're going to use the exact same example, but instead of the researcher wanting to see if it differs than the norm, the researcher wants to see if employees would score better than the norm. So we've changed it from different, which is non-directional, to greater than, which is directional. Everything else is going to be the same, except we are now going to do a directional test instead of a non-directional test. Let's actually get through that. So now here you've got a big difference in that instead of equal and not equal, you've got less than or equal to and greater than as our signs. So it is now a directional test. Step 2 is exactly the same. However, step 3 changes because we are now doing one-tailed directional instead of non-directional. You do not have to say all of this that I've got here. You could either just say one-tailed or you could say directional. You can say all of it if you want, but one-tailed or directional, either of those is fine. Step 4 is exactly the same. Our alpha hasn't changed, our n hasn't changed, and degrees of freedom is still not applicable. And step 5 is exactly the same. That's because all of these values are independent of whether it's the hypotheses are directional or non-directional. From this point on, things will change, but up to this point, we don't, nothing is changed for calculating our z observed. Getting to our critical though. Now our critical is all of the alpha is in one tail. So all of the 0.05 is in one tail. Now, to find this value, you go to your z-score table, and in your z-score table, you find 0.05 within the table. If it's a cumulative table, 0.05 is going to be on this end, but again, it's symmetrical, so finding 0.05 would give you negative 1.645. Since it's symmetrical and we're looking at the upper tail, we just turn that into a positive 1.645. Most charts only go to 2 decimal places, and this is one of those important ones where you go halfway between, because it's halfway between 1.64 and 1.65, so it's 1.645. These are actually the two most important numbers you'll have in z-scores. That is Alpha equals 0.05, non-directional, the critical is going to always equal 1.96. Directional, the z critical is going to equal the absolute value of 1.645. If you're looking for less than, it's going to be negative 1.645. If you're looking for greater than, it's going to be positive 1.645. I put absolute value signs there, but let me actually change that to plus or minus. It's going to be plus or minus 1.645. Whereas the 1.96 is always absolute value because it's non-directional. So again, if you went to the chart, you'd get that, but it's easy if you just have these two numbers written down somewhere, remember them. I'll actually put them on when it comes to the quiz, I'll put that on the top of the first page just so you've got it easy access, because with z-scores it becomes very easy as long as you're always using an alpha of 0.05. It's going to be these two values. When you change your alpha, it's going to change these values, but these are the two values that are the most popular two numbers in z-scores because they are the alphas, alpha 0.05, one direction and two directional critical values. So now we've got 1.645. And this is going to come back to why I said that 1.667 for our observed value is kind of important, because it's between two numbers. That is it's not greater than 1.96, but it is greater than 1.645. Therefore, we would reject HO. So, same numbers, everything is the same, except we're doing a directional test instead of a non-directional. And you see, with everything the same, doing a directional test, we reject. Non-directional test, we didn't. And this goes back to what I was talking about last week when I said, why do we do a directional test if we can? Because it's easier to reject. If we can. We need a hypothesized reason to do it. And this is the way I'd state step 8. So again, that given alpha of 0.05 and the z equals 1.667. But now we're saying we reject HO and conclude that there is statistically significant evidence that the average score of employees is greater than the norm. So now we're stating that we've got evidence that the alternate is true. We never state that we wouldn't say reject HO and conclude that the average score of employees is greater than the norm. That's too strong of a statement for research, for science. Science dictates that we don't prove it, we are just supporting it. Since when we reject HO, we're finding supporting evidence for our alternative, so we are saying that there is statistically significant evidence that the alternate is true, in a sense. And these are important words here, statistically significant, especially the word significant. If you reject HO, somewhere in your step 8, you need to have the word significant. If you fail to reject HO, you should never use the word significant. Significant is a word reserved for rejecting HO in statistics. Significant basically is another way of saying that you rejected HO. So don't use significant if you fail to reject. Use significant every time when you reject. Okay, let's change gears for a minute. We're going to have, it's similar but different now. Now, what do we do so when we know the population variance, we do a z-test, because the standard normal distribution works when you know the population variance. However, the population variance is rarely known. Almost always in stats, in science, you're not going to know a population variance. You are going to have to then estimate the population variance. How do we estimate the population variance? We estimate the population variance based on our sample data. This is something we did. Why did we do earlier in the semester? You remember when we were doing population variance, we took it one step farther and did the unbiased estimate of population variance. That when we just took that from our sample data, The whole reason we learned how to do that early in the semester is for this exact moment, for this reason. And that is, when we don't know the population variance, we instead estimate it. Our test statistic comes what you see down here at the bottom, but I'm actually going to show you a way. Either you're going to be given this, you'll either be given this estimate here. Let me see if this will work. Yep, you'll either be given this estimate here, or if you need to calculate the estimate, I will give you the slightly longer formula that'll show you, and we covered that last week. That was the why you did that on part of the homework last week, and one of the last things that was in the slides last week is just basically how to calculate all of this, how to get to this point with the extra steps in there. Either way, when it comes to your homework and when it comes to the quiz, you should have, between the last week's slides and this week's slides, you should have all the different formulas you need to calculate your observed statistic. So what is our observed statistic? What is our observed statistic? Because it's not linear, I'll actually get back to the observed statistic in just a little bit. What is the difference between a z-test and a t-test? Well, a z-test is a standard normal distribution. It is a standard distribution. It is standardized, meaning it's always going to be the same. It doesn't vary from sample to sample. Sample size does not change the shape of the standard normal distribution. However, if we don't know the population variance and we need to use a t-test, the resulting distribution is not completely normal. It is slightly off from normal. And it is slightly off based on n, based on sample size. So what's going on here? We're now doing, what is a t-test? What is the t from a t-test? It's actually known as the student's t distribution. Interestingly enough, the word student here doesn't mean student as in a stats student came up with this or something like that. No, he was a student he was a grad student at the time, but his last name of the person who came up with this test is named student. So it's the student's t-test because the person who came up with its last name was student. With this t-test, this t distribution, it has a mean of 0, just like the standard normal distribution. However, the standard deviation decreases as degrees of freedom increases. What do I mean there? I mean that as you've got two distributions here that are symmetrical, and my writing's really bad, but the standard deviation increases, or in a sense decreases. So we've got 1 and 2. So 1 is the one that's more spread out, that has a larger standard deviation. 2, the standard deviation has decreased, it's got a smaller standard deviation, it's less spread out. In number 2, it'll have a larger degrees of freedom. So the degrees of freedom determines, in a sense, the kurtosis, how spread out or how flat or peaked the distribution is. It's still symmetrical. We don't have skewness here, but it is peaked or less peaked depending on the degrees of freedom. So there is a different distribution and, in a sense, a different chart. So the z-chart, that was one chart, and it always stayed the same. For the t-test, there is a different chart for each different degree of freedom. So as degrees of freedom increases, the t distribution approaches the standard normal distribution. On the next slide, I'll show you the one chart that is there's a reduced chart that merges all of the charts together, or many of the charts together. And the next slide after this, we'll look at that. Okay, well, what is our observed t? Our observed t is when we use that formula. So we're going to end up using this formula here most of the time, because I'll give you the estimated population variance, which is what this is. I'll give you the population variance estimate. However, if you need to calculate that, again, you just go back to those formulas from earlier to calculate that. Our degrees of freedom for a one sample z-test. So we're doing again a one sample t-test. The degrees of freedom for a one sample t-test is always going to be n minus 1. Our degrees of freedom will change from when we do different tests, but the degrees of freedom for a one sample t-test is n minus 1, n being our sample size. And then you use the t-critical chart by looking at your degrees of freedom, your level of significance, and whether it's one-tailed or two-tailed. So look at your alpha, your degrees of freedom, and one-tailed or two-tailed, and from there you can obtain your critical value. Here is the chart, and this is the chart that I'll just attach this to the quiz. But when you're doing the homework and whatnot, you can come back to this. And what's the important information here? First off, and we'll do it in blue, we've got our degrees of freedom here. So this is our degrees of freedom. These values over here. And one thing I'll point out. So you've got degrees of freedom starting all the way up at 1. Rarely are we going to have 1 for a t, but you've got degrees of freedom all the way from 1. It goes to 30, then it jumps to 40, to 60, to 120, and then infinity. You should always round down if you don't have a value on the chart. So if you, let's say you've got a degrees of freedom of 59, you would then round down to 40. If you've got degrees of freedom of 39, you round down to 30. If it's not an exact value you have on this chart, just round down. If you've got another chart that shows all the values, if you've got an online calculator that gives you your critical value, just use the exact. But if you don't have an exact, you should always round down. The next thing I want to point out is all the way at the bottom with this infinity line. That is when it essentially reaches the normal distribution. And what you'll see here is if you go over to the right, you've got that 1.645 there and that 1.96. Those are the two from earlier. So as you approach infinity, it approaches normal. You're never going to use those for a t-test because you always round down, but again, the point is that as your degrees of freedom approaches infinity, your t-distribution becomes the same as the standard normal distribution. So that's the first thing to use. The first thing to use is your degrees of freedom. The next thing we need to determine is it directional or non-directional? Is it one-tailed or two-tailed? And that is, and we'll use purple for this one, that is what we're looking at up here, whether it's one-tailed or two-tailed. So one-tailed or two-tailed, the top row is going to be one-tailed, the next row is going to be two-tailed. Now that you've determined if it's one-tailed or two-tailed, you need to find your alpha. Your alpha is these values that you have along that first or second row. And I told you as far as I'm aware, I'm going to always use 0.05. The homework might once or twice use something different, but I tried to go back and make sure everything was 0.05. On the quiz, definitely everything will be an alpha of 0.05. But you find this is 0.05 for one-tailed, and this is 0.05 for two-tailed. So what is going on here? For here, we've got, or how would you now read this? Let's say we had a degrees of freedom of 10. So degrees of freedom equals 10. We have a alpha of 0.05, and it is a directional test. So one-tailed. A one-tailed test with an alpha of 0.05 and a degrees of freedom of 10. So first we're looking up in the purple box, we find one-tailed. We go over to where green of alpha of 0.05 is. And then from there we drop down until we line up with our degrees of freedom of 10. And you get this value in here. I'm trying not to mark up this too much so you can use it when you're not just listening to this. But you get this value here of 1.812. So the t critical there would be 1.812. Let's say you were doing alpha equals 0.05, but in this time you're doing non-directional, so two-tailed, and degrees of freedom still equals 10. Well, now you have to go again to the purple box, look at two-tailed now, so that's the bottom one. Find the green, which is 0.05, and that's our second blue one. And in this case, we're still doing 10, but now we're doing the t critical equals 2.228. So you see here in the middle that dark blue, that's already dark blue because that's the standard alpha that's out there is 0.05. If you still have problems with reading this chart, send me an email, ask the instructor on Blackboard. Either way, I want you to be able to read this because we're going to be doing things like reading charts like this for the rest of the semester. Let's use an example now. So, same situation as before. The same exact situation before, except the population variance is unknown. So we must be estimated, and the population variance estimate from our sample is now 225. I use that number specifically because you'll see that it comes out very, very similar to what we did before, but our population variance estimate is 225. And the reason why that's the case or why that's interesting is because that's exactly equal to the population variance in the previous problem. So in this problem, we don't know the population variance, but we use the population variance estimate. That's the same thing. So our example was that it was greater than. Now on 2, we're doing a t-test. So it's a one sample t-test. See, I write the t is funny because that's the t will be in italics. Step 3, it's one-tailed, it's directional. Step 4, now we've got step 4 is slightly different. Step 4 is slightly different because even though our alpha is 0.05 and our n is the same, we now have a degrees of freedom. T-tests always have a degrees of freedom, so you have to put the degrees of freedom here. And then we do the math for this problem. Doing the math for this problem, we get that same value. That's because I set the estimated variance to be the same as the population variance. When they end up the same, you get the same result. But an interesting thing's going to happen here, and we'll see that on the next slide. So now we need to go back to that table and find our critical value, our tree critical value. And you see here, there's one thing, and I'll come back to, I'll actually bring that up again in just a minute. But our t observed value, if you remember, was 1.667. There it is. What's important here is how you write the t. So t with degrees of freedom of 24, I was going to point this out on the last slide, but I'm already past it, equals 1.667. That's the technically right way to write it in APA style, is you write the t, then you write the degrees of freedom in parentheses lowered in subscript, and then it equals 1.667. Let's go back to step 6 though. If we go to, and it says Appendix D here, that isn't going to work for I don't believe it's Appendix D in this book, but the T chart. So if you go back to the T chart, the T critical chart, find degrees of freedom of 24, find alpha of 0.05 with the directional test, you end up getting a T critical of 1.711. Here we look, 1.667 is less than 1.771, so we would fail to reject. Writing it out in a similar way, given an alpha of 0.05 and a t with our degrees of freedom of 24 equals 1.667. Everything after that is the same. We just put that t with our degrees of freedom in there. Now, what's going on here? Important thing to note. When we did a z-test, the exact same test but a z-test, We got the exact same observed value. We rejected. But when we did a t-test, we failed to reject. Why is that the case? That's the case because a t-test has less power. A t-test you're less likely to reject because there's more variability within it because of the changing distribution due to your degrees of freedom. If instead of having 24 participants here, we had 1,000 participants, even probably 100 participants. If we had 100 participants, our critical value would be lower, and our critical value might at that point in time drop below our observed value, and then we would reject. So that's where I said before, as sample size increases, power increases. Well, that's one of the reasons why, because we become more certain. There's less variability, and because this is in a sense a probability test, and we're only rejecting when we deem that the probability is low enough to feel confident, 95% confident to be specific. Well, in this case, it is what's the word I'm looking for? With a lower sample size, we are less confident. As our sample size increases, the probability, the odds of it being variable decrease, and therefore we become more confident, and that's why our t-critical will decrease as we get larger. T-critical will decrease as our sample size gets larger. Okay, the next thing we're going to do is correlation. I'm going to go a little bit quicker on this because this lecture is already longer than I'd intended. So in this, again, just like before, we get the directional and non-directional hypotheses, but in this we are using this is our correlation population symbol, so the correlation of XY, and then this is our hypothesized correlation. So this is either going to be a value between -1 and +1, or it's going to be 0, and which is still between -1 and +1, but that's a differentiation that we'll make. The reason that this differentiation comes in is because whenever we're dealing with a hypothesized correlation of 0, the sampling distribution of the correlation is a normal distribution. So whenever we're dealing with the correlation here of 0, our actual correlation is a normal distribution. In that case, we use the t-test because the variance of the sampling distribution has to be estimated. However, if our correlation is any value other than 0, anything between -1 and +1 that isn't 0, the distribution is skewed, and because the distribution is skewed, what we do is what's called a Fisher R to Z transformation. And the Fisher R to Z transformation, okay, the slide skipped ahead, and I'm not going to go back to it. Just note that if we're comparing to a value other than 0, we use the Fisher R to Z transformation, and that gives us a population variance. So in that case, we can use the Z distribution, the Z test, and it's just because it's going to be the variance is going to be known. What you see here is, again, why is this the case? What is going on with what was on the last slide? Well, you see in the middle, our row, or our population row, is population correlation. Our population correlation, if we're comparing to 0, it's normally distributed. If it's negative or positive, if our correlation we're comparing to is negative or positive, you see that it becomes skewed in the other direction. So if we're comparing to 0, we use the t-test, and we're going to use t with degrees of freedom. And as I said earlier, our degrees of freedom for a one sample correlation test, t-test for correlation, is equal. The degrees of freedom is going to be equal to n-2. So here we're going to have degrees of freedom of n-2, and you use the t-chart again, just like before. You use that exact same t-chart for this problem, using n-2 as your degrees of freedom. your alpha of whatever you're looking at. So typically going to be 0.05, alpha of 0.05, and whether you're doing one-tailed or two-tailed. So in this case, if we were looking for a correlation greater than 0 or less than 0, specifically one or the other, it would be directional. If we're looking just if the correlation's significant, another way to say if the correlation's significant is if the correlation is different than 0. A correlation of 0 means there's no correlation. So if we're looking to see if there's a significant correlation, we're trying to see if the correlation is not equal to 0, which is a non-directional test. This is actually a relatively easy test to calculate, but to do this, you need to be given the correlation, and that would be the R. So you need, in the problem, you'd be given it. We'll see that in a problem coming up in just a little bit. And you'd be given the correlation. Now, what else do you need? You need the N. So in this case, this is actually a pretty easy formula here. I'm talking more on the slide than I probably need to. It's just the correlation times the square root of n minus 2 divided by the square root of 1 minus the correlation squared. So just the correlation squared is there. And this down at the bottom, you don't have to pay attention to too much. We'll come back to this. But why is degrees of freedom n minus 2? And that's because we're using 2 statistics instead of 1. And part of calculating the correlation is calculating what's called the sum of cross products. So that's the sum of squares x, y. And to do that, you need to use 2 variables. Because you're using 2 variables, 2 degrees of freedom becomes n minus 2. If you were taking more advanced stats classes, I'd go into more of what degrees of freedom means. For the purposes of in here, just note that it's the amount of basically freedom that a variable has. And in this case, the variable has freedom of n minus 2. As I said before, whenever you're using a correlation other than 0 as the hypothesis, in this case you would use a z-test. You'd use a z-test because you do what's called the Fisher's R to Z transformation. How does this work? Well, to do this, you need to take, and let me just bring up everything on this slide. So to do this, what's going on here is our formula is z equals, this is r prime minus rho prime divided by the standard deviation of r prime. Standard deviation of r prime is easily calculated here. It's equal to the square root of 1 divided by n minus 3. N is our sample size. Or 1 divided by the square root of n minus 3. So I'll tend to give you easy numbers, like let's say an n of 28. 28 would be 28 minus 3 would be 25. The square root of that would be 5. 1 divided by 5 is 0.2. So your standard deviation of r prime would be 0.2. Easy numbers there, but what needs to be pointed out here though is, and well, it says the appendix specifically here. Again, that doesn't work for your book. To do this, you need to go online. Just Google Fisher's R to Z transformation, and you'll get all the charts there. I'll actually try and go back in and add the chart to next week talking about it. But Fisher's R to Z transformation, you'd use that chart, and you don't actually, very important, many people make this mistake, here, up here, and here. You're not using R, and you're not using rho. You're not using your hypothesized correlation and your sample correlation. You're using the transformed values. So those primes mean that they're transformed. You take those values, your R and your hypothesized correlation, your rho, and you go to the Fisher's R to Z transformation chart and you transform them to the prime values. So for instance, a r of 0.3 might transform into an r prime of 0.48, something like that. And then you put those in to this to calculate out the z there. But to do that again, you need the Fisher's R to Z table. I don't have that here, but it is online, easy to obtain. So let's look at this. Let's look at some examples here real quick. So first is a researcher wants to know if the relation between the research productivity and teaching effectiveness for university faculty, wants to know if there is a relationship for university faculty members. The researcher obtained a correlation of negative 0.36 between number of publications and average student ratings of teacher effectiveness for a random sample of 30 university professors, conducting appropriate statistical tests. What is going on here? Well, we're trying to see if a correlation exists. Let's switch to the next slide and we'll look at how that looks. If we're trying to see if a correlation exists, our alternate hypothesis is going to be the researchers trying to see if the correlation is different than 0. Because if it's different than 0, that means a correlation exists. Like I said before, correlation is 0, there is no correlation. So if it's different than 0, there is a correlation. Then the null hypothesis is that the correlation equals 0, meaning there is no correlation. This is a correlational t-test because the value indicated in the hypothesis is 0. As I said before, if you're comparing to 0, you do a t-test. If you're comparing to any value other than 0, you do a, if you're comparing to 0, you do a t-test. If you're comparing to any value other than 0, you do a z-test. We are comparing to 0, therefore we are doing a t-test. It's two-tailed, non-directional. Our alpha is 0.05, our n here is 30, and our n minus 2 is 28. We just plug these values in now. So first is our correlation we obtained, negative 0.36. Our n minus 2, the square root of that. Our 1 minus our r squared. So 1 minus negative 0.36 squared. And we end up getting a value of negative 2.044. Then you take from the t-critical chart, you obtain a t-critical value of 2.048. So we need to see if our value we obtained is greater than that, looking at the absolute values. Our absolute value of negative 2.044, which becomes 2.044, is less than 2.048, therefore we failed to reject HO. If it had been greater than or equal to, we would have rejected. So given an alpha of 0.05 and a t with degrees of freedom of 28 equals negative 2.044, fail to reject HO, conclude that there's insufficient evidence, again, insufficient evidence is what we use when we fail to reject, to indicate that there's a correlation between publications and student ratings of teacher effectiveness. If our sample size had been 1 higher, just instead of 30 it had been 31, and it had maintained the same correlation, that negative 0.36, then we would have rejected HO. The critical value would have been less, and we would have rejected HO. Shows the benefits of having larger sample sizes. Let's do another test. The correlation is 0.42 for population of normal adults. Researcher believes the relationship is stronger for individuals with ADHD. Tests a sample of 40 ADHD individuals and obtains a 0.55. Does this result support the researcher's belief? So we are comparing now to a correlation of 0.42, different than 0. So we have to do the R to Z transformation. So in the researcher found 0.55. So our hypotheses are that the correlation is greater than 0.42 because the researcher thinks that the correlation is greater for those with ADHD. In this case, we are doing a z-test because our hypothesized value here is different than 0. This is directional. Alpha is 0.05, n is 40, and degrees of freedom is not applicable when we do z-tests. For here, we've got our R prime and rho prime. And this is where I should point out, so if you remember the R xy equals 0.55 and our rho xy equals 0.42. Why is this important? Because you see here in this problem, you have to do the transformation. If we just plugged in these values here, we have this 0.55 for R, you see it's different in the problem. You see this is not equal to this, and this is not equal to this. That is because they've been transformed. In this case, the R prime is going to be equal to 0.618 using the Fisher's R to Z transformation table. And then the rho of 0.42, the rho prime is equal to 0.448 using the Fisher's R to Z transformation. You see that as the numbers go lower, they actually become closer to the same. So the 0.448 is closer to 0.42 than 0.618 is to 0.55. They get larger and larger as you get more and more different than 0. Again, you have to use the Fisher's R to Z transformation table, and we get a observed value of 1.03. You have to find the Z critical value. It's a directional Z test, so it is 1.645 with an alpha of 0.05. The signs match, but 1.034 is less than 1.645. Therefore, we would fail to reject HO, very similar to previous problems in how we'd write it up, insufficient evidence. Okay, in the next part, and this is the final part, I'm going to go through this a little bit quick because we've already talked about some of this, but we are going to now look at confidence intervals. So we've looked at, okay, what's the probability of an extreme value, but now instead of looking at the probability of an extreme value, instead we wanted to look at, okay, well, we could say that we're different than this, but what is the probability, with a specific probability, what is the range that the actual population is going to be if we don't know the population value? To do that, we do confidence intervals. So a confidence interval is just a range of values centered around a value of the sample statistic that has a specified probability. And it's going to be, let's say it's 95.95, 95% confidence interval. So it's going to contain 95% of values of the population parameter. We could say that if we had, let's say we had a mean of 22 for Detroit Mercy, for a sample of Detroit Mercy students, we could then run a confidence interval and say with 95% certainty the actual average age of Detroit Mercy students is between X and X, because it's going to contain 95% of the population parameter. We can do confidence intervals for any sample statistic, but we're typically only going to do them for the mean in here. You can do them for the correlation too. You can even do them for the standard deviation, the variance, all of those. But for in here, we're going to try to focus on the mean. So what we do is just based on the sampling distribution of a sample mean, we can construct an interval centered around it. It's going to contain a certain percentage of the sample means. In other words, we determine an interval that has a width of a specified range of the sample means are in the interval. So and I've said this quite a few times, so I'm not going to go into it more. We're just constructing an interval that's going to contain 95% of sample means, so we'll be 95% certain in that case that the actual population mean is within that range. So our formula that we use for this, if we're using a Z formula, so if we're using a Z formula, and to use a Z formula, you need to know the population variance. But if we're using the Z formula, we use, in a sense, we've got this, the mean of means. The mean is plus or minus the two-tailed critical z-value times the standard error of the mean. Now we're not going to have these exactly, so we're going to convert them. Let's get to that. So if we center an interval of the same length around the sample mean, instead of the population mean, so if we centered it around the population mean, we'd say 95% of scores are within that. But instead of centering it around the population mean, we're centering it around the sample mean. We know that it's going to cover 95% of the population mean, so that's how we say we have a 95% certainty that the population mean is within that range. And this is where it becomes the sample mean plus and minus our two-tailed critical z-value for 95%. We'll just come back to what those critical values will be times the standard error of the mean. How are we going to do that? Well, there's two ways we can do that. We can do it with if population variance is known. If population variance is known, we just use those standard error of the means. And to use the standard error of the mean, you just use the formula we went through earlier on how to calculate the standard error of the mean from the population standard deviation. So you just take the population standard deviation and you can calculate that standard error of the mean. If the population variance is estimated, we use a t-test just like we're using a t-test for hypothesis testing. And in this case, it's the mean plus and minus the two-tailed critical t-value times the estimated standard error of the mean. And again, you use the formulas we covered before for that. For both of these, you need an alpha. You need a value for alpha to get our critical z or t. The value is based on our degree of confidence. It's going to be equal to, our alpha is going to be equal to 1 minus our degree of confidence divided by 100. What does that mean? If we've got a, let's just look here, we'll do this up here. If we have a 95% confidence interval, 1 minus 95 divided by 100, 1 minus 0.95, our alpha is going to be equal to 0.05. If we have a 99% confidence interval, our alpha is equal to 0.01. If we have finally a 90% confidence interval, our alpha is equal to 0.10. These are the three different values that you'll see for confidence intervals. Sometimes people get weird with them, but these are the three different standards. I try to keep it pretty standard to this 95% confidence interval because of going back, that's that alpha 0.05. But in the homework, you're going to have to do at least a 99 as well, just because it's good to see the differences between a 99% confidence interval and a 95% confidence interval. But it's easy to show. So 99% confidence interval, it's 1 minus 99 divided by 100, 1 minus 0.99, that is 0.01. So this is where you might have to get a couple different critical values for z other than 1.645 and 1.96 when you do a 99% or a 90% confidence interval. On the quiz, I will give you the values for all three of these. It's a very small box that just goes on there that's got the 1.645 and 1.96 for alpha of 0.05, and then it's got values for 99% alpha of 0.01 and 90% alpha of 0.1, so that you've got them all handy for the confidence intervals and for the hypothesis testing tests. So let's look at an example real quick. Or a couple examples. The first example we've got here is, given the following information, we're going to construct a 95% confidence interval for the population mean when we have a sample mean of 108, an n of 26, and a standard deviation of 15. You'll notice here when we look at it that we are using a sample standard deviation. Sample standard deviation. the population variance is not given. I try in the quiz to always say population variance equals this, or population variance is unknown. The sample variance is equal to, or sample standard deviation is equal to a specific thing. However, in this problem, I don't say that. In this problem right here, you see it doesn't say the population variance is unknown. However, the population variance is not given to you, and the sample standard deviation is. So in this case, we are going to use a t-test because the population variance is not given. We're looking at a 95% confidence interval, so the alpha is 0.05. The population variance is not known, so we're going to use the t-distribution. For confidence intervals for one sample, we're going to use degrees of freedom of n-1. Confidence intervals are always two-tailed. If you can read what I'm saying, always non-directional. Two-tailed. Confidence intervals are always two-tailed. They're always non-directional. So when we go to that t-chart from earlier in the slides, you look at n-1, n was 26, so n-1 is 25. We look at degrees of freedom of 25. We're looking at two-tailed, alpha of 0.05, and we get a t-critical of 2.060. So you'll recall from before, our estimated standard error of the mean is equal to our standard deviation of the sample divided by the square root of n-1. So we plug those numbers in. We've got a n of 26, so the square root of 26 minus 1 is 25. Our sample standard deviation was 15, so it's 15 divided by 5, or 3. Now, this is just the first step. If you recall, and I'll bring it up in just a minute, it was the mean plus and minus our two-tailed crit t, that times our estimated standard error of the mean. We only calculated this piece. So it's going to be then the mean, I think I got room here, the mean plus and minus, and if you remember our two-tailed critical t from the previous slide was 2.060, and then that is going to be multiplied by 3. So it's going to be our mean in this case, our mean was 108. It's going to be 108 plus and minus 2.060 times 3. If we factored that out, so the mean of 108 plus and minus 2.060 times 3, 108 plus and minus 6.18, we get, so 108 plus 6.18 equals 114.18. 108 minus 6.18 equals, you see it over here on the left, 101.82. These are the two values for our confidence interval, but how we end up writing it out is what you see here. This is what you should write when doing a confidence interval. You put the lower limit, that's 101.82, is less than or equal to the mean, the population mean, is less than or equal to 114.18. What does that mean? What does this confidence interval mean? This means we are 95% certain that the actual population mean is between 101.82 and 114.18. What does this refer to, or what, before we get to the last example, why do we do a confidence interval like this? Why is this important? So we've looked at null hypothesis testing. We looked at that. That's what we did the first part of this lecture. We looked at taking a null hypothesis, comparing our value using an alpha, and just seeing if it's statistically significant. This is what's called null hypothesis significance testing. There has been a big push in the last 10 to 15 years to move away from null hypothesis significance testing. There's been this push to move towards confidence interval testing instead. Instead of saying this value is statistically significant, you just list the confidence interval and you say, and let the reader decide what is going on there, or let the reader decide whether they deem that it's different enough or not. And another way you can use a confidence interval is in a very similar way. Let's say we were here, so we had this this sample mean of 108. Let's say we wanted to see if we wondered if our sample differed from the national mean of 100. The national mean is 100, the national average is 100. We collected a sample and we wanted to see if our sample differs from the national average. Well, we can do this confidence interval here and look at, does the value we're comparing to, which was 100, is that value in our confidence interval? We're comparing this 108 to 100. The 100 is not in our confidence interval. Therefore, we can deem that we're 95% certain that it's different. That's another way to do hypothesis testing that is not the same as null hypothesis significance testing. Since the value we're comparing to is not within our confidence interval, we can say we're 95% certain that it's different. That type of thing. And that's just a little bit of information about stats and what's going on in the field of statistics, and how there's this big push away from significance testing, specifically null hypothesis significance testing. All right, let's do one more example. Instead of a 95% confidence interval, let's do a 99% confidence interval. A lot of similar things going on here, except now our alpha is 0.01. Our degrees of freedom, n-1, is 29. If we go to the t-chart, we get a t-critical of 2.756. We calculate out our S of x, or we've got our standard deviation of the population, or the sample, or sample standard deviation. We need to calculate our estimated standard error of the mean. We plug in those values again. We get 0.743. And now we can just plug those two values, this 2.756 and this 0.743, into our formula. And we get lower limit and upper limit. The lower limit is 49.95. The upper limit is 54.05. And so our 99% confidence interval is 49.95 is less than or equal to the mean is less than or equal to 54.05. And in this case, just like I was saying, we can say that we are 99% certain that the actual population mean is between 49.95 and 54.05. Okay, I know this lecture ended up longer than I'd anticipated. I got pretty long-winded for a few things. I just love talking about stats. If you still have any questions, email me. Send the questions on the Ask the Instructor on Blackboard. Either of them is fine. I will get back to you. The only thing this slides does not have that I wish it had, and I'll add it for future, but then I'll add it into next week, is that Fisher R to Z transformation. You can just Google that and get that. Thanks. Come on back.